Okay, let's get started, please. So I don't have Wi-Fi on my laptop for some reason, which kind of defeats the purpose of this first slide. I want to start talking about the types you have access to in C. The types are a little bit different than what you have in Java. They look similar enough, they behave a little differently. Okay, so you know what a type is from CISC220 and CISC221, right? So a type just defines the set of values that an object can have and the operations that you can perform with the object. Right, so for the int type, you know that they represent int numbers. In C, like Java, there is a minimum and a maximum value, which I would show you if I could actually click on that link, but I can't. You can do things, you can do arithmetic with int types, right? So you can do add, subtract, compare them, and so on and so forth. Right? Now, if you actually click on that link, you can actually see all of the arithmetic types in the C language. And there's a lot more of them than there are in Java. But I can't click on that. So I'll have to come back to this, I guess, next lecture, which will be next week. Or you can click on it yourself and take a look at it. You'll see that if you click the link, there's a bunch of types, and there's many different ways that you can name the same type, which is very confusing for new C programmers. You'll see something like signed int, and you'll think that's different than int, but it's not. It means the same thing. So there's a table on this page that shows you in the column called equivalent type what the I guess you can call it the standard type name is when you use one of the integer types. And then you'll see all of the equivalent types beside it in the left-hand side. I really wish I could show that to you. Okay, anyway. The integer types behave the same as they do in Java, right? So you remember in Java, you have this issue with overflow, right? So there's a minimum and a maximum value for all the integer types, right? If you exceed that range, you end up with overflow, right? So if you exceed the maximum range, you end up wrapping around to the negative end. If you exceed the negative end, you end up wrapping around to the positive end, right? So they all behave the same in Java because Java basically inherited its semantics from C. Right? The floating point types also behave similarly to Java. So in C, you have the types float, double, and something called long double. Right? So a float in C is the same as the float in Java. A double in C is the same as a double in Java in most cases, right? In most cases. So on your desktop computer, it's certainly the case that they behave the same. Right, so there's really no point in me talking about the integer and floating point types right now. Now, C is weird. So the types, if you look in this table, C is strange in that it doesn't say how big a type is. Right, so you know in Java, an int is always 32 bits. Right? So the language mandates that it's 32 bits. Right? A long is 64 bits. C says that an int must be a certain size or bigger. It doesn't say what the actual size is. It says it tells you what the minimum size is. Right? So that means when you're programming in C, you often have to figure out, well, how big is this object? Right? Which you don't have to do in Java. Right? But in C, it's a problem. So there's an operator called sizeOf that will query the size of an object or type. Right? For example, I can ask for the size of int. Right? And that number will change depending on the architecture that you're programming on. Right? So if you're on a desktop computer, size of int is probably 4, which is 32 bits. But if you're programming on an embedded system, the size of int might be something else. So it could be, it's probably a lot smaller. So it's probably 2. 2? It's probably 16 bits, so probably 2. Right? Or smaller. Could be larger too. Right? So the language doesn't actually say, which was really problematic back in the 90s when there were a bunch of common desktop architectures around. Right, so back in the mid-90s, there were 16, 32, and 64-bit desktops all available to you at the same time. So you'd write a C program, and it would behave differently on all the different platforms. OK, so the size is always reported in terms of multiple of the size of car. So car is it's similar to Java's car. Right? It represents character values. Right? Also the same as Java, it's also an integer value. Okay? In C, the size of car is said to be 1. Okay? So the size of car is always 1. So it's supposed to be here somewhere. Oh, I guess I didn't tell you what it was. Okay. C says that car is the smallest addressable object that you can have. All right, so here's a little program that prints out the size of a bunch of different things. So here's printf again, right? So this is formatted print, right? Now remember, this formatted print function takes in a conversion operator here, right? So percent something, right, tells it to convert this thing according to that conversion. Oh, hang on, I should turn the little laser pointer on. There we go, right? So percent %LD says convert that, whatever size of car is, according to this conversion operator. Okay, so D is integer. LD is a long integer, right? Which is the type that's returned by size of, right? So it's a long integer, so you have to write the LD to get the conversion. If you just write a D, the compiler will complain, right? It'll tell you what the exact problem is, right? Which it didn't used to do back in the bad old days, but now compilers tell you you have the wrong conversion operator here. So that's kind of nice. So there's car, that's going to return 1. There's something called bool with an underscore and a capital B, which I'll explain in a second. And there's a bunch of other types here, right? So there's something called short int, there's an int, there's a long int, there's a float, a double. And then there's the pointer types at the bottom, right? So I've got a pointer to car and a pointer to double. And if we run this program here, which hopefully I have, this is supposed to be size of, which I didn't compile, so just a second. Size of. Oh, no. Size up. Okay, so compile and then run, and it spits out this, right? So it tells you that the size of a car is 1, right? It tells you that the size of a bool is 1, so they have the same size. They take up the same amount of memory. A short int is 2, so it takes up twice the amount of memory as a car, right? An int is 4, so it takes up 4 times the amount of memory as a car. Long int is 8, right? So 8 times the amount of memory. A double is also 8 on my computer. So 8 in this case corresponds to 64 bits, right? 4 is 32 bits. Notice that the pointer types, it doesn't matter what pointer type you have, it's always, on this computer, it's always 8, right? So it's always 64 bits to represent any pointer type. Right, now remember, these are all multiples of whatever car happens to be, right? So if you happen to be on a computer where the size of car is something else, like 16 bits, right, all of these numbers will change to reflect the size of car on that particular computer. Okay, so there's size of. So the Boolean type, so you can kind of guess that underscore bool is a Boolean, right? It has a weird name, right? So it's underscore and then a capital B. Right? Whenever you see something with an underscore in C, that's something that's normally a reserved word of some kind. So it's something that the compiler writer or the standard, the C standard, is mandating. This is going to be a special reserved word, right? So it's underscore bool. Now the reason it's called underscore big B bool instead of little b bool is because before they created a Boolean type, the compiler writers introduced their own Boolean types, and they were often called little b bool, right? So when the standard finally got around to mandating that there should be a Boolean type, right, they had to introduce a different name. Okay, so this thing bool stores a 0 or a 1, okay? So it always stores 0 or 1. 0 is false, 1 is true, right? Just like it is in bash, right? Now, you can actually assign any non-zero value to a bool. Right? So for example, you can assign the value 0.5 to a bool. And the compiler will automatically convert that to true. Right? So any non-zero value gets converted to 1 when you store it in a bool. So I'm going to show you that in a second. Okay. Now if you include the header standard bool in your program, instead of underscore bool, you can use little b bool. Right? And then you can use the words true and false. Right? False is just 0. True is just 1. Okay? So it doesn't matter what you actually, if you use false or true, right? You can always interchangeably use 0 and 1, or 0 and any non-negative, any non-zero value. The Boolean type uses all the same operators that you have in Java, right? So not, and or, they're all the same. There's our little program, right? So here's our variable called flag, right? Its type is bool, and I've set it to 0, right? So that means it's going to be false, right? I have a little if statement here, so if flag is true, I'm going to print true. Otherwise, I'm going to print false, right? So nothing terribly exciting here. Where's my, here? Sorry. No, it's not boo, boo? Yes, it's boo. All right, so it prints false, right? Not surprising because the flag is set to 0 here, right? I now want to play around with this and start changing values. Boo. Okay, so if I change that to a 1, you would expect that to print true, right? Because bool stores zeros and ones. I have to compile this. Hang on. Boo. And boo. Okay. So if I change it to 1, you get true, right? Not surprising. What's a little weird in C is that you can set this to whatever value you want, right? So I can put in a double value here if I want to. The compiler does not complain, right? So I can compile it, and I can run it, and you get true again, right? So the conversion is silent, and it always works, right? You have to be careful about that sometimes, right? So any non-zero value is treated as true. Right? Notice I'm using an if statement to print out true and false, right? Oh, what am I doing here? Oh, sorry. This is using so if I use standard bool here, back here, I don't include the header standard bool. Here, I've included the header standard bool, right? As soon as you include the header standard bool, you're allowed to write little b bool and true and false, right? If you don't include standard bool, right? So if I try to write, watch this, it'll probably work now. So if we try to write that and compile that, the compiler should issue an error. Yeah, so there you go, right? So it says there's an error, true is undeclared. Right? So it doesn't know what it is, so you have to include the header standard bool to tell the compiler what true means. Okay, all right, so there you're going to get the same thing, right? You're going to print false, right, and true. If you change that to true, you'll print true, but the same thing happens. So this is boo 2. Okay, right, so here I've got the flag, so the type is bool, right, and the flag now is not true or false, it's the value 0.001, right? This also works. Right, so, sorry. Okay, so this is boo 2. Right, so that also works, and it's also, the compiler accepts the assignment of a, sorry. The compiler accepts the assignment of a double value to a Boolean silently, right? It doesn't warn you that there's a problem, right? It's perfectly happy taking this to be the case, taking this to be acceptable. All right, now printf has no conversion for Boolean values, which is inconvenient to say the least, right? So where's the, oh, okay, right? So if I try to print out a Boolean flag, right, or a Boolean value, you don't get true or false, right? You have to convert it to an integer, so %d, right? So you have to convert it to an integer, and what you get back are the values 0 and 1, right? Which is kind of inconvenient when you're working with Boolean values, because you'd like to be able to see true and false, right? There's no conversion operator if you use printf, right? So you can use d or I as your conversion operator. Those are synonymous, right? So d and I are both integer, right? U is unsigned integer, which in this case also works. Okay, so that's also, so an unsigned integer is just an integer that has no sign, right? It's always positive. Positive or 0. If you actually want to print out true or false, there's a way to do it, but it's awkward, right? So you can use what's called the ternary operator in C, right? So %s is the string conversion operator, right? So if the thing over here is a string, it'll output a string here. It'll print out a string over on this, when you use %s. Right? If you don't feed it a string, the compiler will complain. So I need to feed this a string, and I want to convert flag to either true or false instead of 1 or 0. Right? So the ternary operator is made up of a question mark and a colon. All right? So the way you read this is, if flag is true, then return the value true. Otherwise, return the value false. Right? So this is like a short if statement. Right? If flag, then true, else false. Right? So the result that's being returned by the ternary statement is the string true or the string false. Right? If flag is true, then you get the string true. Otherwise, you get the string false. Right? So you have to go through a lot of work just to print out true and false in C, which is unfortunate. But that's because it's because back when C was originally created, there were no Boolean values. Everything was zeros and ones. Right? So if you wanted something to be true, it's non-zero. If you wanted something to be false, it's 0. Right? And so printf was never extended to handle actual Boolean values. Maybe one day that will happen. I think the earliest it can happen is in 2023, when the new version of when the new standard of the language is published. But we'll see what happens. Okay, car. So car is similar to Java's car, but it's not exactly the same thing. So car is usually used to represent character data. Now in Java, car always refers to a Unicode value. In C, car is just some 8-bit number. Right? Not necessarily, so it doesn't necessarily use the Unicode encoding. Right? So you have to be a bit careful about that. So car is the smallest addressable unit of the machine. Right? So that just means whatever your computer can natively, whatever memory address your computer can natively address, car is that smallest unit. Right? Usually it's 8 bits. So on most modern computers, it's 8 bits. You can actually find out what that value is if you include the header limits.h, right? And then look at the value car bit. Okay, so like Java, a car literal is any single character inside of single quotes, right? Or it can be an escape sequence inside of the single quotes, right? So single quote, some character, that's a car, right? Single quote, and then one of these things, followed by a closing single quote, is also a car, right? So where's chalk? So single quote, slash, single quote, right? That's the character single quote, right? You have to escape it because the single quotes are being used to delimit the start and end of the character, right? So if you wrote single quote, you get an error, right? Because that's not a car, because there has to be something in between. Right? And then you've got a dangling, unmatched single quote here. Right? So you have to escape it. You have to do the same thing with the double quote. I'll come back to the question mark in a second. If you want a backslash, well, the backslash is the escape character, so you have to escape it as well. Right? And then you've got some other ones here. So the useful ones here are /n, right? That's new line. And then /t is a tab. So those are often useful when you're printing stuff out and you want to, so tab is useful when you're printing stuff out and you want to line stuff up in columns. New line, of course, you need to print a new line character and go to the next line. Question mark. So why is the question mark here? So there's nothing special about the question mark, at least not in Java, right? So why do you have to escape the question mark in C? It's because C's got these weird things called trigraphs. So a trigraph is question mark, something, right? And these get interpreted as some other character inside of a string literal, right? So if you try to make a string out of these, right? So I do this, right? And if this is a valid character, this gets converted into something else. So that gets converted into something else, right? So those are what are called the trigraphs. You can Google it. We're never going to use them in this course, but if you want to know what the trigraphs are in the language, you can just Google for it, right? But that's why that's why you sometimes have to escape the question mark. Okay, so that's the character type. We'll come back to that in a minute when I start to talk about strings. Enumerated types. All right, so C has integer enumerations, right? So if you took CISC220 with me, at some point you were told what the enumerations were, right? If you actually read the notebooks that I provided, you would know that there's something called the int enum pattern, right? So the int enum pattern is when you create a bunch of names and you assign an int to each name, right? That's basically what a C enum is, right? Now the problem is these aren't anywhere near as powerful or as safe as the Java enums, right? So you'll see exactly what happens in a second. All the enums let you do is it lets you assign a name to some integer value, and you use these when you have constants, right, that you want to give numbers, that you want to assign a number to. So for example, right, enum day. So this creates an enumerated type called day, right? And then I've got the list of days, right? Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, right? So that just says that the name sun has the value 0. The name mon has the value 1. The name tue has the value 2, and so on and so on and so forth, right? Here's the enumerated type called compass, right? Now you're allowed to assign values to the names in your enumeration, right? So here I've assigned the value of 0 to north, right? East is 90, south is 180, and west is 270, right? So 0, 90, 180, 270 degrees. And then finally, I've got the month enumeration here, right? And here I've started numbering January with 1, right? If you don't number the rest of the enumerations, then the compiler takes that value and adds 1 to it. So February becomes 2, right? March takes that value, which is 2, and adds 1 to it, so it's 3. And then 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? So once you've got your enumerated names, you can then use them later on, right? So for example, I can write enum day. You have to write enum day. You can't just write day, right? So you have to write enum day. Then you can make a variable, d, and you can assign it one of your enumerated values, right? So I can assign it the value Sunday, for example, right? And then d will have the value 0, right? It doesn't have the string value sun. It doesn't have anything else convenient like you might have in a Java enumeration, right? It's just the number 0. Right? Enum compass dir equals south means that dir has the value 180. Right? And then enum month m equals OCT means that m has the month 10. Right? And if you run this little program, which I probably didn't compile either. I did. Enums. Right? You get d is 0, dir is 180, and m is 10. Right? So they're just int values. Right? That's all they are. And you can actually change them to be some other value if you wanted to, right? Because they're just ints. All right, so that's the enumerated types. You sometimes, you will occasionally see these because they are useful for creating named constants. All right, there's also a type called void in Java. So you've seen void already, right? You've seen void as a return type, right? So if a function says it returns void, that means the function returns no value, right? If a function has a parameter, if a function has no parameters, you can also put void in the parameter list, right? That indicates that the function has no arguments, right? So f round brackets void means that f is a function that has no arguments, right? If you make a function that takes no arguments, you should always use void. To indicate that it takes no arguments. You should not leave blank round brackets. Because believe it or not, the declaration int f with round brackets, right, that does not declare a function f that returns an int and takes no arguments. That declares a function f that returns an int and has some unknown number of arguments, right, some unspecified number of arguments. Right? So if you want to make a function that really has no arguments, make sure you put void in there. The next version of the language, or the one after that, will require you to put void in it. But for now, that will compile just fine. The one down here is dangerous, but very powerful. Right? So you can make a pointer whose type is void. Right? So void star is a pointer that can point to anything. right? So that's a pointer that points to any object, right? Which you can sort of imagine is going to be problematic sometimes, right? If you make a void star pointer and point it to a double, and then you use the void star pointer and treat it as an int, right? You're going to have weird results. But the language lets you do that, and it lets you do some very powerful things, as we'll see later on, right? Okay, so here's a little program. I've got x equals 1. Then I make a pointer to void, right? I just told you that that pointer can point to anything, so I can take the address of x, right, and use that pointer to point to the object x. Okay? Now, can I use the pointer for anything? Well, yeah, you can, right? But you have to tell the compiler, what is this thing pointing to, right? So I can't use p directly, because as far as the compiler is concerned, it's pointing to some unknown object, right? So before you use it, the compiler wants to know what is that object you're pointing to, right? So I cast p to a pointer to int, right? Because that's what it is, right? It's really pointing to an int object. So I have to tell the compiler, what are you pointing to? Yep.
How come the asterisk is on the outside of the bracket?
I'm going to do that in a second. Yeah, no problem. That's good. That's a good question, right? So I have to convince the compiler that p is a pointer to int, which is what the inner cast does, right? Now that I have a pointer to int, right, I can dereference the pointer. So that's what the star does, right, to give me the value that p points to, right? So instead of p, well, imagine instead I had written, instead of writing void star p, if I write int star p equals the address of x, is that right? Yeah. Right. Then remember, to get the value of x, right, you write star p. Right, so we're going to have star p equals 2. We'll change the value of x to 2. Right, so the star in front is the pointer dereference operator. Okay, good. All right. Now, remember, p can point to anything, right? So I can reuse p down here, right? So now I can make a double y, set its value to 2, and then I can have p point to that double value, right? So I can take the address of y and store that in p, right? Now, before I can use p, though, again, I have to tell the compiler what is the type that p actually represents, right? Well, p is actually a pointer to a double, and then I can dereference that value to get the value of p, right? So this will print 1, and this will print 2, right? Oh, LF. So this conversion operator, so this is a double, right? Star something is a double value, right? It's the double value 2.0, right? F is the conversion operator for float, right? So for floating point types, if it's a double, you have to tell printf that it's a long float, which is a double, right? So that's what the L is doing here, right? So LF will print out a double, will convert a double value. F will convert a float value. All right, so if you run this, you'll get 1 and 2, right? That's all. Okay. How about arrays? So arrays in C's have similarities to arrays in Java. Right? They're similar, they're not the same. Okay? All right, so in Java and in C, an array is a contiguous sequence of objects all having the same type. So contiguous means that the objects all sit beside each other in memory. Right? So in memory block 1, there's the first element in the array. Then beside that is the second element. Then beside that is the third element. Then beside that's the fourth element. Right? So that's what contiguous means, right? A continuous sequence. Like Java, C array stores elements of the same type, right? So not like a Python list where you can put anything into the list. Right? Like Java, the number of elements or the size of the array never changes during the lifetime of the array. Right? So when you make an array, you're stuck with an array of that size. Right? But arrays are characterized by their element type, right? So if you have an array of int, that's an array of int, right? It's not an int, it's an array of int, right? If you have an array of doubles, that's an array of doubles. And like Java, you use the square brackets to access individual elements, right? So there is a strong resemblance to how arrays, to Java arrays. Now, unlike the Java array, right, there's no method, there's no field called length on the array. Right? So in Java, you can write a.length, and that gives you the length of the array. In C, that doesn't happen. Right? So the size of the array, so also in Java, when you make an array, normally you use the new operator to make the array. Right? In Java, you can actually declare the size of the array that you want, and that becomes part of the declaration. So I'll show you that in a second. So here we go. Right. So in Java, you can write in C, you can write int x square brackets 3, and that creates for you an array of length 3. Right. So it has that's an array of 3 ints. Right. Just like Java, you can assign the individual elements of the array. Right. So x square bracket 0 is 1, and so on and so on and so on. Right? So this makes the array 1, 2, 3. Right? That's all. Unlike Java, there's no convenient way to print out the array. Right? So in Java, you can use arrays.toString to get the string version of the array. In C, you're stuck writing a loop. Right? So if I want to print out the elements of the array, you've got to do something like this. Right? So if you run this program, it's not surprising what you get. So this is an array. Where is it? It's not open. Okay, so there's the program. Right. So if you run this, not surprisingly, you get the values 1, 2, 3. Right. Okay. Now, how do you get the size of an array? So if you might think that you can use the size of operator. Right? And you would be almost right. Right? So size of some array returns the amount of memory that is used by the array. It doesn't give you the length. Right? It tells you the amount of memory that's used. Right? So how much memory is used? Well, it's the number of elements, or the length of the array, right, times the size of the element type. Right? So if you want to get the number of elements in the array, you have to divide by the size of your element type, which I'll show you right here. Right? So same code as before. Now I'm going to print the size of the array x, right? So size of x, right? Then I'm going to print size of x divided by size of int, right? Because it's an array of int. Wrong one. Here. Okay, so this is array 2, right? So the size of the array is 12, right? So it's using up 12 units of memory. Right? Oh, wait, I didn't print out the, sorry. My program must be wrong. Array 2. Oh, yeah, I didn't print out the printf. So this is size of x. Whoa. Divided by the size of its element type, right? So it's a size, the element type is int. Oops, sorry. So save that, recompile, sorry, GCC. Okay. So now you get 12, and then you get the 3, right? So you have to divide by the size of the element types to get the number of elements in the array. All right, now like Java, when you declare the array, if you want to, so if you know the values that you want to put into the array, you can use an initialization list, right? But you have to do it where you declare the array, right? So here's the array declaration int x, right? On this line, if you know what the values are, you can write equals and then the braces and fill the values of the array. Right? So here's 1, 2, 3. So that's the same thing as, that's effectively the same thing as that. Right? So if you ran this program, you're going to get 1, 2, 3. Now, the initialization list can be shorter than the array size. Right? So if you put the array, oh, sorry, back here. So if you don't put the array size in here, then the size of the array is taken to be the size of the initialization list. Right? So that'll give you an array of size 3. Here, I've said that the array is a size 5, right? But I'm initializing it with the values 1, 2, and 3. Right? And so what C does is it takes the, it uses up all the initializers, and then everything else becomes 0. Right, so this is, oh wait, this is 4, I think. Nope, not 4. 3? Yes, it's 3. There we go. Right? So you get 1, 2, and 3, and then 0 and 0. Right? So any uninitialized elements get set to 0. Okay, now what about a string? So there's no string type in C. Right? So Java's got its own specialized string type. Right? It's got all sorts of methods. Strings have all sorts of characteristics. Right? That's not true in C. So in C, a string is just an array of characters. Right? The end of that string, the end of the array, right? The last element of the array is /0. Right? So that's the character. Well, that's the values. That's the character corresponding to the numeric value of 0. Right? So here I've got the double quotes. Right? So that's a string literal, just like it is in Java. Right? So that's the string CISC220. But at the end of that string is another character whose value is 0. Right? So there's a /0 at the end of this thing here. Right? And then I'm going to put that into an array called str. Right? And I'm not going to specify its size. Right? So if you print out the string using %s, right, that will convert that array into a nice string form, right, and print out CISC220. The length of that string, so there's a function, oh wait, this is wrong. Sorry. You need to include string here. But the program works, so let me just show you the program. Array 5? Yes, okay, so you have to include string, otherwise this doesn't compile. Because I'm using, oh wait, how about array 4? Yes, array 4, here we go. You have to include string because I'm using the function string length here. Okay, so string length, if you give it a char array, will tell you how many characters are in this string. But it doesn't include that terminating character /0. Right? So string length here will give you back 7. 1, 2, 3, 4, 5, 6, 7. Right? 7 characters in that string. Right? That's different than the size of string. Right? So the size of string is how many elements are in this array. That's going to be 8 because there's that extra terminating character on the end of the string. Right? So that's, was that 4? It's 4. Okay, good. Right? So the length of the string is 7. Right? 1, 2, 3, 4, 5, 6, 7. But the size of the array that holds the string is 8. Right? Because you need that one extra character to hold the terminator. All right, so keep that in mind when we talk about strings later on, which will be next week, I guess. All right, now, arrays and pointers in C are more or less the same thing. So the name of an array is synonymous with a pointer to the first element of the array. Right? The subscript operator, right? So when you write square bracket and then some index, that's synonymous with what's called pointer addition, followed by dereferencing. Right? So what do I mean by that? So here's my array, str. Right? I can create a pointer to car. Right? So p star p, car star p is a pointer to car, and I can assign the array to that pointer. Right? So I can assign the array to that pointer. And then I can write star p equals little c. Right? Okay. So a pointer to an array, right, is synonymous with the address of the first element of the array. Right? So star p is synonymous with the address of the first big C in the string. All right? So if I dereference that pointer, right, so if I write star p equals little c, it changes that big C to a little c. Right? Now, I can do the same thing. Right? So remember, I said that the subscript operator is synonymous with pointer addition followed by dereferencing. So p1 is the same thing as taking that pointer p. Oops, wait, that's str1. That's str1. That's str1. So p plus 1, dereference that, is just the I. Right? P plus 2, dereference that, gives you the S. Right? And p plus 3, dereference that, is the C. Right? So this little fragment of code changes the characters capital CISC to little case CISC. Right? Which you can see if you run the program here. Right? There you go. Right? Okay, so it's going to be weird. It's going to be weird when you see this the first time, right? So one more time, right? The pointer p, right? If you make it point to the array, is the same thing as the address of the first element of the array, right? So p plus 1, that's just the address of the second element of the array. P plus 2 is just the address of the third element, and p plus 3 is just the address of the fourth element. Right? If you dereference that address, right, you can change the value that's stored in the array. Right? So arrays and pointers, they're more or less the same thing. Now, the really unfortunate thing about arrays in C is that there's no bounds checking. Right? You're really going to miss this. So you're really going to miss the exceptions that you get in Java. Right? So if you write p minus 1, right, with a Java array, you immediately get an index out of bounds exception. Right? If you try to go past the end of the array, you immediately get an index out of bounds exception. Right? Now what happens if you do this in C? Well, if you're lucky, your program crashes. And if you're unlucky, some object gets overwritten. Right? Why does it get overwritten? Right? Because the indexing is just a pointer dereference. Right? So if you write p minus, so if you do something like str minus 1, that's the same thing as saying p minus 1, which goes to the whatever object is sitting one memory location in front of the array. Right? And then you can scribble over that. Right? So if you're unlucky, some object gets overwritten. So let's see what happens. Right? Same program. Right? I'm going to change the first character of the string to little c. And now I'm going to write p plus 100,000. Right? So I'm going to go to the element number, what? 100,001. Right? So the 100,001th element of this string. I'm going to try changing that to a question mark. The compiler doesn't care if you write this. Right? So this is 6, I think. Let me just bring up the program for you. Right? So if I compile this program, right, the compiler is perfectly happy with this. Right? No errors, no warnings, nothing. If you run it, you get something you get what's called a segmentation fault. There's other types of errors you can get here. Here I'm getting a segmentation fault. Right? So all that you know is that something's crashed. Right? You don't get an explanation of why something's crashed. It's just something's crashed. Right? So in Java, you would get an exception and you'd be told why it's crashing. Here, it just dies, and now you have to figure out what happened. Right? Okay, so that died, so that was good. Now here, it's a similar program. So I've got my array, and then down here I've got another variable after the array. Right? So x equals 100. Now here I go to p plus 8. Right? So there's p0, p1, p2, 3, 4, 5, 6. Right? p7 is the /0. Right? What's p8? Well, p8's whatever's after this array. Right? It's whatever happens to be after that array. Okay? So it's not in the array, it's whatever happens to be sitting after the array. So what the heck happens when I run this program? Right? Now remember, x is 100. Right? Oh, sorry. Down here, I'm going to print out the string and x. Right? So watch what happens. Oh, wait. 7. X magically becomes 63. Right? Good luck debugging that. Right? So, yes?
What happens if you make it 7?
If you nuke the terminator?
Yeah.
So if you nuke the terminator, printf may or may not barf. It might be okay, it might not. Depends. So, So, I mean, the answer to this is just try it, right? The problem is it's not going to be reproducible. So depending on your architecture and, oh, wait, what just happened? Control Z. So the language simply says that the behavior is going to be, you're going to overwrite the terminator. Exactly what happens depends on your implementation of printf, right? Because that's where I'm going to use it next, right? So I'm going to feed that string to printf. So the answer is I have no idea what's going to happen. It might work, it might not. It really depends on what, how printf is implemented. So that overwrites the terminator. And here, so, oh wait, that's interesting. So now you get the question mark. So the question mark emerges, right? It would not be surprising if the program crashed either, because printf is expecting that string to be null terminated. Okay, so there's one other thing here. There's a comment up here, right? So in order to actually overwrite that value, let me put that back to 8, right? You have to compile the program this way. So there's this flag here, -f no stack protector. So I'm going to recompile the program. Oh wait, oh yeah, that's fine. I'm going to recompile the program, and now run it again. Okay. So if you compile the program without telling the compiler, so this turns off this what's called the stack protector, right? So if you compile the program and you turn off the stack protector, you enable the stack protector just by compiling it the normal way, right? The compiler will try to diagnose, not the compiler. The compiler will insert code into your program so that the program crashes. Well, it'll try to insert code in the program so that the program crashes instead of doing something crazy like overwriting the value, right? So here, it silently overwrote the value and changed it to 63, right? Here, right, you now get an error message when it runs, right? And the error message is very funny. It says stack smashing detected, terminated, right? So what's happened is the compiler has inserted some code into your program to try to detect this sort of error, right, where you go beyond the bounds of an array and write something into memory, right? That thing right there is called a buffer overrun error, right? And it's one of the most common security errors that you get in a C program. Somewhere here. So if you Google stack smash protecting GCC, you'll come up with this paper here that came out of the University of Waterloo. And they tell you in great gory detail how the compiler implements this stack smashing protection. Right? So when I was learning how to program in C, the compilers wouldn't do this. And so you would just get, you would either get some error or you wouldn't get an error and something weird would happen. And you'd have to try to figure it out. Right? What time is it? I guess we should stop here. So let's pick up from here the next day. I guess that'll be next week. Right? So don't forget on Thursday you have a midterm, right? Midterm's online. So it's on OnQ. It's like 40 minutes or something like that, 40, 45 minutes. You write it wherever you want. And yeah, sure. Yeah, it's going to be short. I mean, you only got 40 minutes. How much can I ask you? It could be 50, but then, you know, people want like extra time to submit their work, and then you got to get to class, and then all this other stuff, right? So yeah, it's going to be timed to like 40, 45 minutes.